So I'm not making this a bonus, I'm making it required, and I'm giving this video tutorial. So we have this reversible reaction. They are all gases. You could do Kp or Kc. We are using Kc. We have a certain number of moles of each gas. Now the ice box here would work with either moles or molarity, but the idea of Q or K only works with molarity, only works with molarity. Here we get molarity by dividing by the 2 liters size of the vessel. And now we have the molarities here. So which way will this reaction run? When there are zero molarities on one side of the reaction, then the reaction has to run toward the 0 because it couldn't possibly use a 0 capacity, a 0 molarity to run. This has a value for all 3. So it is a question of which way it will run. What we will do is take the Q value, which is the snapshot K. We'll take the Q value and compare it to K. And Q is just using the K math, but for right now. So when this is just starting and it has these molarities, what is the K value? So we're going to call it Q because it's not necessarily at equilibrium. So products over reactants to the power of the number in front, and we get 0.879. Now, K was told us as 0.02. So Q is bigger than K. What that means is that as this settles toward being at equilibrium, the number that we have currently will approach K. So does this need to get bigger or smaller? It needs to get smaller. That means that the numerator needs to get smaller, which means we need to get less products. The products are in the numerator. So the reaction will turn a direction overall that gets us less products. It will go to the left. Reaction will go to the left. Since we know it will go to the left, we now know that we will be losing molecules out of here and gaining them over here. Remember to make this double the amount lost as we are gaining each here because the ratio is 1 to 1 to 2. We need to lose double whatever we're gaining here. It takes destroying 2 of these to gain 1 and gain 1. Also, we can't use a half. We can't use this be 1x and this be half x because when you use fractions and you end up squaring them and so forth and multiplying them, they don't work like whole numbers. For instance, when you square a fraction that's less than 1, instead of going up, it actually goes down. So we're going to use whole numbers. We'll take our K value. When this is at equilibrium, what will we have? Well, we will have the situation where Kc is true. So we have this value. And these will be the concentrations at equilibrium. Now, they're already in molarity because I did that back here. So we're going to put these in. And hopefully we can get out of using the quadratic formula, and we can. This one has the special math loophole that all math teachers would recognize, that I can square root both sides. And that's equal to square rooting the left and then the numerator and then the denominator separately. That you can do that too. So when we do that, here's the square root of 0.02. Square root of that is clearly the same thing inside. Square root of this is the same thing inside. Multiply this times that gives me this, times x gives me this. Consolidate the terms across the equal sign, and we get x. Now, you are not done, and be careful, and it's very tempting to think that you're done, and everybody's made this mistake, including me. What are we looking for? The concentrations of all 3 at equilibrium, but the concentrations are 0.4 plus x. So take 0.4 and add in x, and that is the concentration of these 2. Brackets means molarity, so I have answered the question. You could put a capital M here, but also you have said molarity by writing brackets. And of course, these are the same amount. And HI will be 0.375 minus double of whatever X was, and we get this.